Check 1, 2. In parts 3A and 3B, we're going to explore the laws of conservation and how they relate to the 5 generalized conservation equations that are embedded within the compact form of the Gij, comma j equals 0 equation. Okay. Also, we're going to introduce key concepts that Professor Yibo used to formulate the grand unification theorem, such as new group theory, and how new group theory is associated with symmetry, and then tensors. Gij, comma j equals 0 is a tensor equation, so it's useful to understand on a fundamental level what tensors are. Okay. Now, the intent here is to scratch the surface, and in future episodes, we're going to go into greater detail. Okay, we're going to drill deeper into these concepts and principles. So this is just a primer. Now, the overarching goal here is to demonstrate how to expand the equation into its space-time components for each conservation equation. But before we go there, I want to read an excerpt from Dr. Yibo's book, and this comes off of page 18 of the Grand Unified Theorem. Okay, and I quote, "Obviously, there are many possible group operations to be considered. However, the motivations are the end results or the goals of the global analysis. We need to consider those goals before thinking about possible operations. The global goals and analysis in this work have to do with the development or formulation of a force field theory from which physical laws may be derived. The philosophy would therefore need to be based on some form of absolute conservation laws, which should be so global that processes within and perhaps even outside the universe may be expected to fit in or governed by such conservation laws." Okay. He goes on to state, since we are thinking about force fields, we should expect terms such as momentum, mass, or energy to be useful or applicable terms. Furthermore, the conservation law should be expressed in such a way that it can work well with complete field, particles plus field, or other concepts. The constraints tend to lead us to the concept of flux operations within the conservation equations, end quote. Okay. So conservation laws that Dr. Yibo is referring to in mathematical physics are principles, fundamental ideas that describe how certain physical quantities do not change over time. And that's what the 0 at the end of the equation represents. Does not change, it's invariant. Okay. Conservation laws are crucial. Why? Because they're crucial in understanding the behavior of physical systems and are often expressed in terms of symmetries. Okay. So the goal, as Dr. Yibo stated, was to develop a force field theory that could explain all physical phenomenon in the known universe and even beyond the known universe. Okay? So the GAGUT equation expresses that all mass, momentum, and energy is conserved at every space-time point in the universe within the unified field. Okay? All right, so within the grand unification theorem equation is embedded the universal conservation equations, which are in turn associated with universal conservation laws, which we're going to break down very shortly. Okay, so the I in the equation represents the conservation equation related to the conservation law. And this goes back to what we talked about earlier, that the I represents God's material in the form of energy, matter. Okay, so again, conservation laws in physics are fundamental principles, okay, and that state that certain properties of isolated physical systems remain constant over time. Okay? And these laws are crucial because they help us understand and predict the behavior of physical systems. And they apply to a wide range of phenomena, stuff we see every day, to the dynamics of stars and galaxies. So these are the key conservation laws. Conservation of mass states that all the mass within an isolated system, such as a universe, is conserved. Okay? And in fact, mass and energy are interchangeable. So according to the special theory of relativity formulated by Albert Einstein, mass and energy are interchangeable. Okay? And that's a form of transformation, transforming from mass to energy or energy to mass. Okay. Conservation of momentum states that the total momentum of a closed system, such as the universe, remains constant if no external forces act on it. Okay? And momentum is the product of an object's mass and velocity. When you multiply an object's mass times its velocity, then that's momentum. And conservation of energy states that energy cannot be created nor destroyed, only transforms from one form to another. All right. Next, group theory and symmetry. So group theory is a branch of mathematics that studies symmetry. And symmetry in physics refers to invariance under certain transformations. And group theory provides a framework to describe these transformations. Okay, so let's break that down a little bit more. Okay. I want you to note that the comma in the equation Gij, comma j equals 0 does not just denote transformations between mass, momentum, and energy, but also represents transformations in mathematics, which involves changing the position, size, or the orientation of a shape or function on a coordinate plane. Okay? So these are the four main types of transformations. We have translation, which if you take a shape and every point moves in the same direction, that's called a translation. It's like, let's say, sliding the shape without rotating or flipping it. Okay, we can move it anywhere as long as all the points move in the same direction. That's type of transformation is called a translation. Rotation is when you turn a shape around a fixed point, known as the center of rotation. Okay? The shape itself doesn't change, but its position does. Right? So the points on the shape, they're rotated around a fixed point called the center of rotation. Okay, the next type of transformation is called a reflection. Okay? So reflection, this flips a shape over a line, creating a mirror image. So the line of reflection acts like a mirror. Okay? And lastly, dilation. Dilation is when you resize a shape by expanding it or contracting it while keeping its proportions the same. So let's take a square, for instance. If you resize the square by expanding it, even though it's getting bigger, the sides of the square remain the same because, of course, square has equal sides. So you're maintaining the proportions, but the shape's orientation remains unchanged. Now, these transformations can be combined to achieve more complex movements and changes. For example, you might, let's say, rotate an object and then translate it to a new position. Okay, so this is what group theory studies, symmetry. Okay, you can move this in either direction. So rotation, translation, you can do a reflection, which basically if you have a line, you put a line here, this object is just reflected about that line. So it's like it's looking at itself in the mirror, hence the term reflection. Okay. Next in 3B, we're going to look at the laws of conservation and the generalized conservation equations that are embedded within the Gij, comma j equals 0 equation. we start with Gij, comma j equals 0, which is this is in its compact form. This is the compact form, and tensors allow us to write it like that, okay? For example, these are the i's, and the i's are going to represent the conservation equation that relates to the conservation law. Okay, so, and just to note that you can have as many dimensions as needed. We're only going to be working in 4 dimensions: time, and these are the space dimensions, spatial dimensions. Okay, so we're only going to work in 4 dimensions, so we're going to use this compact generalized conservation equation. So this is what the time component of Gij, comma j, this is the x component, y component, and z component. So we have 3 spatial dimensions and 1 time dimension. Okay. Okay, so firstly, we assign a 0 for I to represent the generalized mass conservation. Okay, so we have a 0 in place there. Now, for momentum, we have to keep track of direction of a particle or object because momentum is a vector, and vectors have both magnitude and direction. Okay, so for the momentum, we're going to have 3 components. Okay. Again, vectors are defined as an object that has a magnitude and a direction. Okay. And the 3 spatial directions are x, y, and z. So we're going to assign a 1 for the x direction, okay, in this case, and then we'll assign a 2 for the y direction and a 3 for the z direction. So you want to pay attention to the i's. I left the mother equation up. So we have mass conservation 0, momentum in the x direction 1, momentum in the y direction 2, momentum in the z direction, that's 3. And note that all of these are the same. Down, 0, 0, 0, 0 goes with time for j. The j are the space-time dimensions, remember? So you have time, and then 1 and x are associated, 2 and y are associated, and 3 and z are associated. So that's why we're able to write the Gij, comma j equals 0 in such a compact form, because you look at the pattern, right? All these have common denominators. Okay, and lastly, for the generalized energy conservation equation, we assign a 4. Okay? And there we have it. I sincerely hope that this presentation gives you more of an intuitive sense of what the equation is representing, which is conservations, is that at every space-time point in the universe, the unified field is conserved. The unified force field is conserved. Okay? All right, so in part 4, we're going to look at potential group operations and the general tensor. And this will give us some deeper insight into how Dr. Yibo formulated the theorem. What was his thought process?